Electrostatic potential energy. When work is done against a conservative force like gravitational force, it gets stored as potential energy. Let's consider a body lifted vertically to a height h from Earth's surface. Some work has to be done against gravitational force of the Earth to lift the body, which is stored as potential energy in the body. When the body is released from height h, the body gains kinetic energy and loses an equal amount of potential energy. The law of conservation of energy holds good in this case as total energy of the system is constant. Like gravitational force, the electrostatic force between two charges at rest expressed by Coulomb's law is also a conservative force. The gravitational force between masses m1 and m2, separated by a distance d, is expressed as g m1 m2 upon d square, where g is universal gravitational constant, which is equal to 6.67 into 10 to the power minus 11 Newton meters square per kilogram square. We can say that the gravitational force F is inversely proportional to the square of the distance between the masses. Similarly, the Coulomb's or the electrostatic force F between charges Q1 and Q2 separated by a distance d is expressed as kq1q2 upon d square, where k is constant, which is equal to 1 by 4 pi epsilon naught. We can say that the electrostatic force F is inversely proportional to the square of the distance d between the two charges. We observe that both gravitational and electrostatic force obey the inverse square law. We know that the work done against gravitational force is stored as gravitational potential energy for the mass in the gravitational field. Similarly, work done against electrostatic force is stored as electrostatic potential energy in a charged particle in an electric field. Let us now discuss the electrostatic potential energy of a charged particle in an electric field. Consider the electric field of a positive charge Q placed at origin O. Let Q naught be a positive test charge located at point S. To bring the charge Q naught from point S to point P, closer to charge Q, some work has to be done against the force due to the electrostatic field Fe. The external force F required to move Q naught should be just about sufficient to overcome the electrostatic repulse Fe on Q naught. Therefore, we can say that the magnitude of the external force is equal to the magnitude of Fe, which is equation number 1. The external force F should not give charge Q naught any acceleration. Therefore, the net force on Q naught is 0. The charge Q naught must be brought from point S to point P at very low constant speed. The work done to move Q naught from point S to P is denoted by WSP and is stored as electrostatic potential energy for charge Q naught. Therefore, electrostatic potential energy for Q naught is equal to WSP. If we remove the external force F, then the charge Q naught moves away from Q in the direction of the electric field and gains kinetic energy, such that the gain in kinetic energy is equal to the loss in its electrostatic potential energy. The sum of kinetic and potential energy of charge Q0 is always constant or conserved. We know that the work done by the external force F to move charge Q0 from point S to P is denoted by WSP. This is equal to the integral of external force F times dr in the limit S to P, where dr is the distance between the 2 points, which will be equation number 2. We know that from 1, magnitude of external force is equal to magnitude of Fe, but the direction is opposite. Therefore, the external force will be equal to the negative of Fe, which will be equation number 3. Now, from equation number 2 and 3, we get WSP is equal to negative integral of Fe dr between the limits S to P, which will be equation number 4. Let potential energy of Q0 at point P be given by UP. UP means the potential energy of Q0 at point P. And the potential energy of Q0 at point S be given by US. Work done by the external force WSP is equal to negative integral of Fe dr between the limits S to P, which was equation 4. In that case, WSP will be equal to UP minus US, which is equation number 5. Work done by the external force WSP will be given by delta U, which is equation 6, as delta U means the change in potential energy. Work done by the external force WSP is given by delta U, which was equation 6, where delta U is equal to UP minus US, that is equation number 7. Now, the difference in electrostatic potential energy between 2 points in the electric field of any arbitrary charge distribution will be equal to the work done to move a charge from one point to another. The work done according to equation 7 is independent of the path followed to move Q0 from S to P without accelerating Q0, and is dependent only on initial and final positions. Hence, the electrostatic force Fe is conservative, and work done against electrostatic force Fe is independent of the path followed. Now we add constants on both sides of equation 7. So adding a constant C to the electrostatic potential energies will not alter the difference in electrostatic potential energy between them and the work done WSP. Distance between the charges Q and Q0, if it is infinity, then the electrostatic potential energy of Q0 at point S is US, which is U infinity, will be now 0. So work done by the external force WSP, which was UP minus US, will now become WSP equal to UP minus U infinity. As U infinity is 0, so WSP will be equivalent to UP. equation number 8. We mark that as equation 8. Based on equation 8, the electrostatic potential energy of Q naught can be defined as work done by an external force to bring a charge Q naught from